All right, with that, I think I'll go ahead and announce our speaker. So thanks everyone for coming to our last space seminar of the semester so far. My name is Jason Schuster, Assistant Research Professor here at UNH, and very pleased to welcome Dr. John Dorelli, who actually has some UNH experience in his background as well. So John, actually going back to his undergrad, actually got his BS in physics from Purdue University, after which he then received his PhD working with Jack Goddard over at the University of Iowa, I believe. And then after that, he made his way over to Los Alamos during the postdoc years, and then ended up here in our very own Space Science Center, as a matter of fact, for about 6 years, I believe, before then going to his current affiliation at NASA's Goddard Space Flight Center. Today, John's going to be talking to us about the MARBLE project, one of my favorite acronyms, as a matter of fact, in our field. So with that, I'll give the marble.
That's not saying much, considering.
We have a lot of different acronyms, but I'll roll the marble over to John to
Easy.
Yeah. All right, thanks, John.
Well, thank you, Jason. So Jason reminded me that it's been about 15 years, I think, since I've been here. My wife insists that I did visit at some point, but I don't remember. So I hope that doesn't mean it wasn't a memorable experience. But, I know I did maintain connections with a few folks here after I left. This project was actually funded by a Living with a Star Strategic Capabilities grant. And I was involved in the previous round of that. I think it was probably like 10 years ago or something like that, a long time ago. And it was to do exactly the same thing. It was to build a global magnetosphere model that had, electron scale physics and, beyond MHD. And I guess NASA decided they had to do this again. I'm not sure why, but we were lucky enough to get funded. And I think in the last round, in the last project, I don't remember what my role was. I think it was mainly to argue with Jimmy about whether MHD was a good model. And so I don't think we've come to conclusion on that. And in fact, if anything, I think I've come a little bit full circle, but not fully full circle, because I think in the intervening years, as people have tried to move beyond MHD, it hasn't been entirely successful. And I'll say Kai's group has been an exception to that. And I'll take a little bit of credit for pushing you guys to simulate magnetospheres other than Earth, because I think that was key to find something that was doable on computers at the time. And so they have, the souped up version of OpenGDCM that can do Mercury, Ganymede. I don't know if they've tried Earth yet. Earth still, I think, is a little bit out of reach. But the way people are working on this now is to basically throw the kitchen sink at it. And so the Michigan group, the Space Weather Modeling Framework, they have this thing called embedded PIC, where they're basically trying to just take fluid simulation and embed PIC everywhere that you need PIC. Very expensive. They still have trouble resolving, electron scales, and that's sort of the goal here. So I thought it would be good to try to take a step back and ask the question, what is the physics we're after? And what is the minimal amount of physics that we have to include in the code to capture that? Because, there's MHD, which has its problems, and then there's these sort of kitchen sink models that are have too much information in them, quite frankly, and are too hard to simulate. So the problem that I focus on is, if I can get it to work. Okay, there we go. Oh, okay, magic. So the problem that I focus on is kind of the holy grail of magnetospheric physics, or one of them anyway, is to really, if your code can reproduce an auroral substorm and like make a movie like that, but be a simulation, then what else is there really to do with magnetospheric physics at that point, if you can do that? But as you can see, this is very complicated. There's a lot going on many different scales. All of this stuff maps to stuff that's going on in the magnetosphere. And there have been arguments for like 60 years about how that stuff in the magnetosphere works and maps to the ionosphere and makes all these auroral forms. I think MHD is actually making a lot of progress on this. But as you'll see by comparing two different simulation codes, there's a lot of work to be done, right? So on the left is Gamera. This is part of the MAGE framework. And this, I think the primary developer here is Kareem Sarafi at this point, who is really kind of is spending his time trying to simulate every mesoscale structure known to exist. And he's just sort of made a list. I want to do auroral beads. I want to do omega bands. I want to do streamers, all kinds of, stuff that you see in the aurora, and is just kind of like checking the boxes and saying, MHD can do this, MHD can do this. So I'd like to take a step back and say, well, is that really true? So if you look at on the left here, so superficially, these two things look, forgetting about the colors. I mean, you get the nice Kelvin-Helmholtz instability, you get turbulence in the tail. There are some differences that matter though. So in the Gamera simulation, if you'll notice, you see these little kind of undulations happening at the transition between the tail-like field and the dipole field. And these are, if you look at auroral images, often you'll see that prior to substorm onset, the growth phase arc, this thing here, kind of breaks up into these little blobs here. These are called auroral beads. And we don't really know what's causing those, but they seem to be often associated with substorm onset. And then the thing sort of breaks up and you get an expansion of the aurora, and then later on, you'll start to get these streamers coming in. So Karim was focused on the beads. And he said, okay, I see that because of this huge density gradient here, if I resolve my MHD simulation enough, I can actually get kind of an interchange instability happening here. And it really has very little to do with the fast flows in the magnetotail that are thought to drive substorm onset. So Karim would say these are just kind of an afterthought. They happen. It's just a coincidence that it's happening because of these, it's happening during substorm onset. It's a feature of the thinning of the current sheet. But what you'll notice in the Gamera simulation is that the fast flows are coming from off to the left here. So beyond about 40 RE. And that's not typically where people think reconnection in the tail happens. People, from spacecraft observations, it seems like the canonical location is about 25 RE or something like that, not 40 RE. So that's something they kind of sweep under the rug. It's like, well, we can't really explain why reconnection onset is happening way out there. I have some ideas about that, and because if you look at other simulations, particularly ones that have some form of resistivity in them, it doesn't matter what kind. You do get an intense, pretty intense current sheet that forms at the dipole transition region, and you get a reconnection onset there. And then what happens, it kind of expands tailward and you start to get fast flows coming in and you get the substorm expansion. So there's something happening inside. There was a big debate for a long time in the substorm community. Is it something happening inside and then propagating out, or is it reconnection and then propagating in? That's the inside out versus the outside in. Now we think there might be an inside, outside, inside story about how substorms happen. But you can see these are two fundamentally different pictures. And when I talk with them about it, Karim about it, reconnection onset doesn't happen here. But it may be just because of the numerics in their scheme. They have a very high order scheme, no resistivity. There's no reconnection happening at the dipole transition region in their code. Go ahead.
So
By the way, please interrupt.
these are both MHD, but one has resistivity and one's like,
Yes.
is that the difference? Okay.
Different grids, basically different resistivity models, because Gamera is relying on numerical resistivity and it has a very high order scheme. And, some of these other codes have explicit resistivity. You have different choices of resistivity.
And what's the rough location of where the enhancement in the current sheet happening?
I'm sorry, the rough location of what?
Where
Where
the
this?
enhancement,
Yeah, okay, so this is typically about between 10 and 15 RE is where that happens. And that, people will also argue with that as well. That's too close, right? You should have reconnection onset happening at about 25 RE. And that, a lot of people think that reconnection onset produces a fast flow that when it hits the inner magnetosphere, that causes substorm onset. So there's a lot of stuff.
Well, observationally, there's been reports, reconnection onset as close as 7 RE.
Yes, and things depend on the solar wind conditions, how long the IMF is
Depends on a lot of
southward,
things.
right, it depends on a lot of
On
things. I would argue that typically the dipole transition region is an interesting place if you have constant driving, where if the resistivity is right, you can actually have reconnection onset occurring there. And the dipole transition region can move very close in under very strongly driven conditions. So it's not, I don't want to pick a number RE, it's really the transition between the dipole field and the stretch
Okay,
field.
we get that. I mean, a second comment, I mean, there's one model that you didn't use, and that model. I have published the beads 20 years ago, I mean, and associated with interchange or ballooning instability, and also.
Yeah, I mean, I didn't mean to exclude you. In fact, that's just illustrative of the fact that there are lots of different opinions on this still, even though everybody's using the same physics model. So that might lead you to think, is there physics that we're missing? Because these codes are getting down to very small scales now. They're getting down to scales where you start to have to think about what other physics do we need to include. And so one of the obvious things, right, so this talk is about the aurora, so we have to talk about particle precipitation. And we usually don't think of a direct connection between magnetic reconnection and the aurora. Particularly from an MHD perspective, reconnection happens, then some motions happen in the magnetosphere and they drive field line currents, and then you make an aurora. But we've known for a long time that reconnection itself is a source of particle precipitation, and people study this with low Earth orbiting satellites all the time. And they even try to look at the shapes of these precipitation patterns. These are ions on the bottom here. This is the MSP data. And by looking at these kind of low energy cutoffs and time of flight effects, and I'll go into more detail about these, you can actually infer some of the properties of reconnection. So these particles are directly connected to the reconnection process. The other interesting thing that people notice is that because the electrons travel along field lines much faster than ions, there's a decoupling of the electrons and the ions. So you might expect some interesting electrodynamics occurring because of the decoupling of the electrons and the ions, field line currents that are directly driven by reconnection. This has been completely untouched by researchers to this day. I mean, nobody has really kind of taken these kinds of things and tried to figure out what are the field line currents that these are producing, and how is that related to the sort of fluid-like picture of field line current generation that we have. This, I think, gives us a clue about what additional physics we need to add into the MHD codes. We have to, at the very least, reproduce these things, and it would turn out that in order to do that, we don't have to go too far away from MHD. This is just to show that you get the same kinds of things on the night side. And what's interesting, they just have a different acronym. We love acronyms. They're called ion dispersion events on the day side. They're called velocity dispersed ion structures on the night side. And they've been kind of studied independently, but they're exactly the same process. You've got reconnection somewhere happening. And these particles will precipitate, and as they stream toward the ionosphere, they're also drifting perpendicular to the field. That's the reconnection rate. And so you get these time of flight effects. So helpfully, this is inverted, the way the DMSP data is usually plotted. So here's the dispersion. It goes from high energy to low energy. And what's interesting about this is that if you look in the literature, you find that people have done statistical studies of these events and compared them to things like inverted V's and superthermal electron bursts that are causing discrete aurora. And there's a relationship between the two. So when you see these, often just equatorward, you'll start to see this region of inverted V's, and they're really tightly coupled. So that gives us a clue. There's some relationship between discrete auroral arcs and these VDIS events that are known to be directly connected to reconnection. So there is a direct connection here between reconnection in the magnetosphere and particle precipitation that can generate discrete aurora. And this is sort of the physics motivation for how do we modify our MHD codes in order to capture that physics and explore that physics. So I think I probably need to speed up here, but so I won't belabor this point, but I'll just say we already know some places in the magnetosphere where MHD goes wrong because we couple different models to the MHD codes. We put kinetic physics in there. So we know that when MHD is good when E cross B drift dominates everything, all the other perpendicular drifts. But once you start to have this slowdown, MHD breaks down. And you have to take into account all the energy dependent drifts. You have to kind of plug in a ring current model, some kind of drift kinetics model in the inner magnetosphere where MHD is breaking down. But this is not really satisfying because it's just sort of an abrupt change. You have E cross B drift dominating, and then very abruptly, magically, okay, now it's no longer. Now there is no E cross B drift, and it's essentially like static equilibrium. So there is a transition there that is where there's missing physics. And this is known in the community that we're missing this physics of the flow breaking region, but there isn't a good alternative to MHD to capture this. You can imagine this is going to be very difficult to do something, particularly if you have like something out at 50 RE or something with a full pit code, right? You don't need a full pit code. There's got to be some kind of intermediate model. And that's the question mark. So what I would suggest is that we should just extend this region out and find a model that handles both the high flow regime and the low flow regime seamlessly, so that you can actually model the deceleration process. And it turns out, if you do that, if you extend drift kinetics out here, you get a couple of things for free. You get particle precipitation, you get parallel electric fields, in addition to all these energy dependent perpendicular drifts. And so in principle, with a modest extension of MHD, you can handle the flow breaking region and model the parallel acceleration, parallel electric field and particle precipitation simultaneously within one mathematical model. So that sounds simple on paper. What I hope to convince you is that this makes intuitive sense and that there is a path computationally to do this that is much simpler than going full pick, and that we can actually have hope of doing this in an Earth scale magnetosphere on present day computers. Okay, so this just briefly, I want to show you, get into a little more detail of the physics of field aligned current generation. So in the MHD, I think one thing that people love about MHD is you can make all these kind of intuitive cartoons about what's going on, right? The field is frozen to the flow. So you can just imagine plasma flowing and dragging these like rubber bands around and twisting them. And that's how you generate field aligned currents, right? If you have some flow vortex here, you will twist the magnetic field and that will generate a field aligned current. And that field aligned current will be carried by an Alfvén wave to the ionosphere, and depending on the conductivity of the ionosphere, you'll get some energy reflected back, so that this motion gets coupled with ionospheric motion. So that's the basic physics of why motions in the magnetosphere drive motions in the ionosphere. You twist the field, an Alfvén wave propagates, it transmits an electric field to the ionosphere and makes it move around, and then you get a reflection, many reflections, until those two things become coupled together. But I think what MHD does a great job of the perpendicular motion, the E cross B motion. Where it fails is in the parallel transport part. So what we know is, and Mike Shea, I think, was one of the first to point this out, is that you also have waves propagating away from the reconnection site that are generating field aligned currents. And it's very simple. For example, in Hall MHD, instead of the field being frozen to the ions, the field is frozen to the electrons. So if you have electrons making current, the field will be distorted and that will generate a field aligned current just because of the reconnection, just because of the existence of a current sheet. And there will be some pointing flux that propagates parallel to the field. And so you can get field aligned currents coming directly from the reconnection site, even in a fluid picture, without even worrying about particle precipitation. So that's already very interesting. If you could do a global Hall MHD simulation, and these days you still can't, I mean, it's still very difficult to do that for an Earth-sized magnetosphere, you might get a completely new set of field aligned currents that are in superposition with these classic region 1, region 2 current systems that MHD can give you. So that suggests, okay, at least we should do Hall MHD. And that should be much easier than PIC simulation. Just going back to previous work, there are a lot of groups now doing planetary magnetospheres that are smaller than Earth's magnetosphere and recovering some of these effects. So you can actually see these field line currents generated by reconnection, and you can see them propagating to the ion, to the surface, in this case Ganymede, producing this kind of rippled structure in the field line current pattern. We do often see this in Ampere data. MHD doesn't do a very good job of reproducing these things. You know, you can raise the question, are we missing some current systems that might be tied to reconnection during substreams? I think if we could only expand our magnetospheres to Earth size, and do a direct comparison with this, that would be quite interesting. Okay, so that you could think of that, what I just showed you, as the wave picture of magnetosphere ionosphere coupling. So you've got motions in the magnetosphere, they propagate as waves, they carry field line currents as waves, it's just Alfvén waves. And that's how you understand the aurora. You've got some current source, and so you need a parallel electric field because you've got a current source in the magnetosphere. And electrons then get accelerated in that parallel electric field. This is typically, you know, so if you look at some of the earliest work on how a plasma can support parallel electric fields, the famous Knight relation from 1970, I forget what year it is, it's 72? 73, okay. That was basically the idea. But now let's get back to this particle picture. So we've known for a long time, like I said, that reconnection also generates particle precipitation and field line currents just because of ballistic free streaming particle effects. No electrodynamics at all, right? So if you just have a source of particles here and there's reconnection happening, so there's an electric field out of the plane. As the particle drifts parallel to the field, it's also drifting perpendicular to the field. So it will mirror, come back, but some other location in the source will also reach that point, and you'll get these asymmetric counter-streaming populations. That's really just it was kind of an amazing thing, this Ansauger paper predicting these things, these observations, and you can actually see them in the data. So you might think, okay, that's all that's going on. There's just free streaming particles, nothing interesting about that. Well, as you can see, these distribution functions have pressure anisotropies, they have field line currents, they have heat fluxes, all those things. And they're highly non-Maxwellian. There's no way that MHD can accommodate distributions like that. So what is going on? How do we incorporate this into our models? It turns out that Colesrid in 1983 produced such a model. It's called kinetic MHD. So it's just MHD, but with parallel transport. So the perpendicular motions are E cross B drift, and the parallel motions are just parallel transport. And the way this works, and I apologize for the explicit math, if we were gonna unify the wave and particle pictures and include these reconnection generated waves, somehow we have to extend the Colesrid kinetic MHD and make it kinetic Hall MHD. So what I would argue is that probably the minimal model that can capture all of these things, E cross B motion, dispersive waves and Hall MHD, and parallel particle transport, is called kinetic Hall MHD. It turns out this model doesn't exist. We've got kinetic MHD, we've got Hall MHD. There's no regime of validity of Hall MHD. It's just not valid anywhere unless the plasma is very cold. And so we know that in the magnetosphere, the plasma is not a very low beta plasma in the region plasma sheet of interest. So we need some other model, and it doesn't exist in the literature. So we went digging and into all the drift kinetics literature, and oh my gosh, it's terrifying. I don't know if any of you have tried to go through some of these papers, but you know, it all started with this Little John paper, right? So there's there's classic guiding center theory, but what the modern way that people do guiding center theory is it's sort of like high energy. We become high energy physicists. We write down some Lagrangian, and then we look for transformations of that Lagrangian that make it more symmetrical so we can ignore some of the coordinates, like the gyrophase, for example. And then we do a coordinate transformation. So we have some distribution function. This is our full distribution function. And we're changing the coordinate system to this new coordinate system where it's the parallel velocity and the magnetic moment. And in this case, the magnetic field, importantly, can be time varying and spatially varying. So you can have, Alfvén waves. And it makes it non-trivial how to go from this coordinate system to this coordinate system. So if you assume that the plasma is strongly magnetized, you can expand this way. So you have some gyrophase independent piece, and you have a gyrophase dependent piece. And then all of this kind of gory, horrible math. And what you end up with is, this is the thing that I think we're all familiar with. You end up with the drift kinetic equation that describes the evolution of the gyrotropic piece of the distribution. And so you've reduced the dimensionality substantially. There's the magnetic moment just becomes kind of a label for these independent equations. But you basically have the spatial coordinates and the parallel velocity coordinate. So already this is much easier than a full PIC simulation. And it's going to capture a lot of the physics that we're after for field line current generation and auroral acceleration. Here's where MHD comes in. And this was a revelation to me because, when I sort of grew up learning this stuff, you learn about the collision dominated version of this, right? So you say, okay, the distribution is close to Maxwellian. There's some small perturbations, and then you just do classical fluid, classical transport theory. And if you can neglect the heat flux and the pressure anisotropies, you end up with the ideal MHD equations. So you kind of start from the collision dominated perspective, but the collisionless perspective, you don't really get exposed to because deriving the equations from that perspective is very, very difficult. So the way it works is you have to keep this piece, you have to keep the non-gyrotropic piece of the distribution function. And it turns out, if you go through the gory mess of the perturbation theory and calculate this thing and all its gyrophase dependent horrific mess, and you take moments of this thing to calculate the perpendicular current density, you get this equation, which is kind of amazing. So you basically just all works out that this momentum equation is recovered. So this looks very familiar. This looks like the MHD momentum equation with some corrections to it. This is, you need to have pressure anisotropy. Sorry?
CGL, right?
No, it's not CGL. This is not CGL. This is the momentum equation. The point, that's the very point. It can't be CGL because there are heat fluxes parallel to the magnetic field. So what Coleridge says is that I should just solve my MHD equations, but at each step, I have to solve a parallel drift kinetic equation on every field line to calculate the pressure anisotropy and the heat flux. Then I have to plug that back into here. So I get a coupled set of equations. So I get the usual continuity equation, momentum equation. The Faraday's law looks pretty much the same. This is a Hall MHD version of Faraday's law. We have to include the paraelectric field. That's essential. And so this is what we mean by kinetic Hall MHD, and it includes, and I think this is what isn't often appreciated, it includes the non-gyrotropic piece of the distribution function. That's essential to keep that. So if you wanted to, you could do an MHD simulation, kinetic MHD simulation, and then you could calculate the non-gyrotropic piece of the distribution function, and you can then go MMS or something like that and compare with data. So it's a very different perspective of how to derive the MHD equation. I need to speed things up. So one of the things that makes, so I think the primary difficulty with this approach is as soon as you have a drift kinetic equation parallel to the magnetic field, then you get Landau damping. And if you have a parallel electric field and some kind of wave structure that's propagating parallel to the magnetic field, Landau damping is going to happen. And this is another revelation to me was, you go to the textbook explanation for Landau damping, You know, usually see a little stick figure surfing on a wave or something like that, and, you know, some particles are getting accelerated by the wave and some are getting decelerated, and if the particles gain energy, the wave has to lose energy, and that's your kind of physical picture. But what's really going on is something like this. So if I have if I have in position, in the vertical axis and velocity, if I start with some Maxwellian distribution with some density perturbation, and I just solve this simple one-dimensional kinetic equation, very quickly, on the Landau damping time scale, this is what's gonna happen, right? And the reason is because if I just do Liouville's theorem and follow these parcels of phase space density, these fast particles are gonna zip along, and these are gonna go a little bit slower, these a little bit slower. This whole thing gets distorted, but then you have another minimum here that's coming in superposition. So all of the phases of the wave kind of get mixed up after a time. It's called phase mixing, and this is why Landau damping happens, because if you were to integrate this in velocity space, you get all this kind of destructive interference of the density, and the density just slowly goes away. And so you know, if you have this initial spatial density structure, it will damp away, and this velocity space structure will take its place. So you get conservation of entropy, but this is really hard to model numerically. So you need a lot of resolution in velocity space, even for a simple 1D problem. And you quickly run to the grid scale very quickly. So that's the primary challenge of doing something like this, but it absolutely has to be done, because you can't just, MHD will just have sound waves propagating all over the place. It just, you know, they don't damp away, but any sound wave, acoustic wave, this is gonna happen very quickly. And the thing is just gonna kind of damp away. So we don't know what the impact of that is globally, because we really can't resolve this kind of stuff on a global scale yet. So there's a code out there called Glaciator that's attempting to do this, although I have never seen them show an example of how they deal with the velocity filamentation problem. It's kind of swept under the rug, so you get this huge numerical dissipation that's happening. It is totally dependent on your grid scale, and we don't know what is the correct resolution to be able to capture these effects. So this is just another long-winded way of saying that we haven't solved this problem yet, and we're working on it. But yeah, there's a whole literature on how to do this. So the second part, how are we doing? You know, one of the goals of Marble is to kind of move beyond this sort of proprietary code way of doing things, where we have a few universities that have some codes and people are working at those universities. And if you want to do something and you're not kind of in that orbit, you go to the, you know, community coordinated modeling center and get some crappy low resolution run. But if you want the real, you want the real stuff, you gotta go work with those people and dig into some code that's been, you know, legacy code. And believe me, I've been there, I've done that. It'd be much nicer if these codes were open source and easy to use by people that weren't kind of experts in this stuff. Because if you're gonna learn computational MHD, even MHD, that's really hard. It's a long learning curve to learn about how to build one of these codes. So it'd be nice if there were an easy way for just a person to get involved with this, where they could get access to the source code, have lots of nice documentation, be able to install it and run it trivially on their laptop, run it in the cloud, run it up, you know, this would be very cool. So what we decided to do was go completely from scratch and do everything in Python. And so the first thing, you know, someone would say was, that's crazy. How are you going to actually do a high performance code in Python and make it fast and comparable to something like, you know, a compiler language like Fortran? And it turns out, and I actually only discovered this a few months ago, when I first got into Python and GPU computing back in 2010, there was really no choice. If you wanted to sort of do a code, write a code and make it comparable, you know, get the most speed up out of it on a GPU, for example, you had to write it in C, in 2 to C, and you had to learn all that stuff. And it's kind of painful. It's another learning curve just to kind of get your code to run on that architecture. And so when I first started this, I was like, well, okay, how do we wrap Python into CUDA? And I, of course, was taking the, 10-year ago approach of trying to do it all by hand. Chris Bard, who's been working with me on this for over a decade now, was like, no, don't do that. There's, if you just pay attention to the most recent developments, there's easier ways to do this now. And it turns out all you have to do is take a loop. You don't have to worry about vectorizing or anything, just unroll the loop, write a little, put a little decorator there for number, and it will compile it and make it as fast as your C code, or probably not as fast as Fortran with an optimized compiler, but way faster than the pure Python. And even better, if you want to do it on a GPU, you can just do this thing called 2Pi instead of NumPy. And if you do something like this, it will automatically compile a CUDA kernel for you. And you can get speed ups comparable to if you just wrote it in CUDA yourself. And just, I didn't believe that when Chris told me that. So Chris was like, let me show you. And so he just really quickly whipped up this example. This is just sort of classic Orzag-Tang vortex. On the left is an anisotropic MHD Briou shock tube, just to sort of benchmark the algorithm. And on the right is a 2048 squared Orzag-Tang written in Python, just using those function decorators, so that it can run on a CUDA-enabled GPU. So on a single A100 GPU, we got about a 50 times speed up of that code, comparable to what we were seeing when we were writing it in pure CUDA. So this just completely opens up for everybody, I think, who can program in Python, being able to take advantage of this. So I think it really is, the time is right. And so here's an example that illustrates the importance of reproducibility. So back in 2012, that's also one of the goals of doing it this way, is, once you're in the Python community, there's a whole culture of, I need to be able to take your code on my machine that might be a completely different architecture and just completely reproduce the results instantaneously. So there's all kinds of infrastructure in place that, like containerization and whatnot, that allows you to do things like this now. So there's no excuse for not being able to reproduce somebody's results exactly. And so we found this out the hard way. In 2012, we wrote this paper on turbulent reconnection, just in Column MHD. We published the paper. And then just a few weeks ago, I asked Chris, can you reproduce this with your code? And he went to the paper. And the first thing we found were typos in the paper. That does not help. And we didn't know we knew there was a typo, but we didn't know where the typo was. So like, is this the typo? No, let's run it. Is this it? No. So finally we realized, okay, we had a GitHub repository that we could resurrect to see the old code and compare it to the one we were trying to benchmark against. And there was one parameter that had been set differently. So for some reason, we decided to change it. Neither of us knows why. We did, and when we put it back, it was able to completely reproduce our results with the new code, which is kind of amazing to me. So completely different numerical methods, different code, different compilers. I consider the code properly benchmarked, since it has reproduced these previous results. So okay, so that's. By the way, I missed the most important part, was that the way we're doing this is we had an old finite volume Column MHD code that we resurrected, ported to this Python. And that's sort of one thread of development. The next thread of development is we have to, so that's the MHD part. Now we have to do the kinetic part, which is how do we solve the transport equation parallel to the magnetic field. And as you can see from that phase mixing example I showed you, even with a simple one-dimensional problem, that's not a trivial problem to solve numerically. So imagine doing this in a 3D magnetosphere. So we're taking baby steps.
What were those papers there? Underneath the scheme of the pictures, are you using these in your new work, or are they just?
So no, for the finite volume, so these are just the numerical methods we're using. I'm sorry I didn't go into that. So for the finite volume scheme, we're using this. That's for that anisotropic MHD Briou shock tube. For Hall MHD, we're using this TOF algorithm. And I can't say enough good things about this paper because it really is the only way to do finite volume Hall MHD and make it stable. I mean, I can't, people have been pulling their hair out doing this, and TOF basically, so here's how you do it, and if you just code this in, it works. So I don't think there is another one out there that is actually as robust as this one. Okay, so for the kinetic part, this is kind of a busy diagram. So we very quickly realized if we were doing this in the magnetosphere, we can't do the entire magnetosphere. And nor should we do the entire magnetosphere. We have to adapt our grid to where that physics is actually important. And so the obvious thing to do, because we're trying to model particle precipitation through the aurora, is to define our grid based on the inner boundary, right? So we have some inner boundary. We know where the auroral zone is. We know where those field lines, for any given time step in the simulation, we know where those field lines go. That's the subdomain that we have to worry about kinetic MHD. Everywhere else, we could probably get away with it. But near the magnetic separatrices, basically, that are connected to reconnection, that's what we have to do. So the very first step is we need to be able to integrate guiding center trajectories on this grid. And the way this grid is defined, we have just a spherical polar grid, some patches of spherical polar grid on the inner sphere. And then we just calculate field lines. And then we just define field align grid. Hope that makes sense. And so all of these green points here are grid points. We call these guiding center points. These guiding, and this is a tricky part that we discovered that was unexpected for us, is that if I have some background MHD simulation, because we don't understand all of the kinetic processes on sub-Larmor radii scales, we have to have some kind of subgrid model of current sheets, like resistivity or something like that, or an embedded PIC simulation or something. Because if we integrate guiding center trajectories and we just integrate them through these current sheets, we get the wrong answer. And I'll explain why we get the wrong answer, show you examples of that. You have to stop the integration at these current sheets and then figure out some kind of boundary condition for the guiding center distribution. This is a very difficult and unsolved problem. We haven't solved this problem. But what we do that actually does a surprisingly good job is if we take these current sheets that MHD produces, and we just say, okay, let's just assume there's a Maxwellian distribution function that's isotropic there at that density and temperature. And that's not actually a bad approximation. If you look at PIC simulations in the diffusion region, the distribution functions don't look terribly complex, right? You get some kind of like Maxwellian looking distribution function. It's away from the diffusion region that you start developing these anisotropies. Okay, but you can argue with that, but let's just assume we do that. At each of these points, we integrate the guiding center, guiding centers back until they either reach a boundary of the simulation or one of the current sheets. And we stop the integration at a point where the guiding center theory breaks down. So that's kind of arbitrary. We say, okay, the thermal Larmor radius divided by the length scale of the magnetic field, which is essentially a measure of the perpendicular current, is above some threshold, we stop. And it does a surprisingly good job of identifying these current sheets in the system. And then we just use Liouville's theorem. So at this point, not assuming that the MHD fields are just a constant background field or just a time-dependent background field, we're just back integrating particle trajectories. And then eventually, we would calculate the parallel heat flux, pressure anisotropies, E parallel, and feed that back into the MHD simulation. That's what is involved in doing a fully kinetic MHD simulation. Okay, so here's an example of where what we're trying to do here is make a comparison with low Earth orbit particle precipitation data. And and this is interesting. So what we're doing, we were doing this work in support of the Tracers mission, and Tracers is trying to measure these ion dispersion events in the cusp. And it's gonna get thousands of these observations and be able to do statistical analysis to figure out the properties of reconnection. But when we try to do this, so we're in the cusp here, we take some point where some observation point, the spacecraft, and integrate a bunch of different energies. And the different energies go off in wildly different directions. And so what you're seeing at any given observation point are particles that are coming from a huge region of the magnetosphere. And showing up in superposition. This is exactly like the phase mixing Landau damping picture, right? You've got structures, you've got stuff coming from many different locations, showing up in superposition in velocity space, so you get this kind of banded structure. This is kind of what people call overlapping dispersions. It's that effect. You've got different structures coming in, showing up in superposition in a given observation point. And so when we did this, we found 3 overlapping structures. And this had not been observed. So when I talked to Karl-Heinz Trattner, it has not been observed. So double dispersions have been observed, but not triple ones. This may seem like, why do you care? Actually turns out to be a big deal, because when people that look at these things are trying to explain how you get the overlapping dispersions, the leading candidate for this is that you must have multiple reconnection sites. Because if one reconnection site produces one dispersion, then if you get 2 dispersions, it must mean you have 2 reconnection sites and they overlap. So 3 was a little bit hard to explain, because they don't have, they kind of struggled hard enough to figure out their topology to get the 2 reconnection sites at the magnetopause. How do you get 3, particularly ones that are widely spatially separated? It kind of wreaks havoc with people's simple model of how the magnetopause topology works. So what we suggested was that we're not just seeing reconnection. What we're seeing are current sheets in the magnetosphere. Anywhere there's a current sheet in the magnetosphere, that's a source of guiding center particles. And that has to be part of your boundary condition. So some of these particles are coming from the subsolar magnetopause. Some of them are coming from what we'll call an internal cusp current sheet. Then there's an external cusp current sheet. And these things have very simple explanations. So this part of the cusp current sheet is just part of the magnetopause. It has to be there to deflect the magnetosheath around the magnetopause. Everybody understands this one. This one is a little harder to explain. And it's caused by reconnection, but it's not directly associated with reconnection. What happens is you have a reconnection outflow. It runs into the lobe. And you can actually see the field lines being bent in the opposite direction by this outflow. And it makes a current sheet here. And that's what's actually causing these things. So when I first showed this, a grad student working with us, who'd been looking at the DMSP data, said, hey, look what I found. And it looks very much like the triple dispersion. And we showed this to Karl-Heinz, and Karl-Heinz was, what the heck is that? I haven't seen those before. And then we said, we think it's coming from the cusp, and Karl-Heinz said, no, it's not. It's got to be another reconnection site. And so there it stands, right? So how we test this idea is going to have to await statistical analysis, which Daniel, the grad student, is in the process of carrying out. So for different IMF orientations, because we predict these triple dispersions to be happening when the spacecraft is just below the cusp. So there's a magnetic local time dependence of what types of overlapping dispersions you see, and this is just now being explored. And we'll have to, yeah, go ahead.
If it's not reconnection at these current sheets, that's a source of these more energetic particles. What is the source?
That is the big question, right? So if you look at the cusp, you look at, you wouldn't, this is part of what's causing the difficulty, is at the subsolar current sheet, you can kind of project the field and get an X-type thing. And people will say, yes, that's reconnection, obviously. But once you get up here, particularly the southward IMF condition, it's hard to know what that is.
Well, it has to be a authentic discontinuity, it has to be a rotational discontinuity. I mean, and that goes all the way back to Gosling's paper and the D-type distributions. I mean, that's basically what you see.
So I don't think I would categorize this as a rotational discontinuity. So, and let me explain why, because, and so another group that's also involved in tracers has been looking at this kind of stuff. Brandon Burkholder and Katerina Nikari has been looking at how can you energize particles in the cusp. And they have a very interesting paper out with Antonius Otto that shows that you can have parallel electric fields existing in these current sheets in the cusp. So you have to understand somehow the dissipation mechanism going on there. It's not just a rotational discontinuity, you know, that's alphanically propagating and you get the D-shaped distribution. There's something more interesting going on. And so it also guiding center theory is breaking down there. So goodbye D-shaped distributions,
Well,
right? I mean, guiding center theory is totally breaking down in these current sheets. They're thin current sheets. And they have parallel electric fields. So like, you know, people like Michael Hesse and those folks would say, oh, all I need is a parallel electric field and then I have reconnection. So you could say, yes, I have some form of reconnection happening there. But it's certainly not the type that people are trying to explain these dispersive events with. And so there's a lot of resistance actually to this idea that could be a source of particles. So, and I mean, like, there's resistance, right? I had Stephen Fuselier telling me, I think there's something wrong with your code. It's that, to that point. So I think the only way we'll understand this is if we can, A, get a handle on whether these are real. And I'll be the first to admit, this is just an MHD simulation, right? So we don't have all the kinetic physics that supports these sub-Larmor radius scale current sheets. So we need to have a better understanding of what's going on in these current sheets.
And
More work to be done.
and does the current sheet really bifurcate like that, or?
It does. It does, because this current sheet is caused by the Magnetosphere flow. This current sheet is caused by the reconnection outflow.
Well, I mean, this is.
Go ahead.
I just have a question about the model. It makes sense to me that like in an ambient plasma population that you'd have maybe E cross B drift dominating in the perpendicular and then, you know, parallel could have maybe the kinetic drift. But when you enter like, you know, transition region or just even if you're in the tail and there's turbulence, couldn't you have a considerable perpendicular kinetic drift as well? So like in.
Yeah, so I'm sorry, I'm being a little bit messy here. So these simulations are kinetic MHD in the Coulthard sense, in that there are only E cross B drift and parallel drift. And that's all you need to reproduce these kinds of things.
Oh, okay, I see.
All right, so.
But yes, you're absolutely right. I mean, in general, you have to, you know, particularly, but see, the problem is, and I'm sorry, the problem is that you have kinetic MHD being valid here. Once you get in these current sheets, not only do the ions decouple from the electrons perpendicularly, but they become completely demagnetized. So there is no regime in which you would say, okay, I just have these drift kinetic separations valid. Now, probably in the dipole transition region, you would, but for something like this, we need a full model of at least the ion kinetics to get the boundary condition for the drift kinetic piece.
That makes sense.
I mean, this is what Himju did in her thesis, I mean, 50 years ago.
Oh, Hunju disagrees with this too.
Right?
Hunju disagrees with this too.
No, I mean, she used particle tracing, I mean, and.
Oh, she did. Yeah, lots of people use
Yeah,
particle
and she
tracing.
got the same result
Yeah.
as you, I mean, and she classified where do the particles come from.
No.
How many eddy particles?
Jimmy, I share an office with her at Goddard. We talk about this stuff. So no, she does not agree with this. So yes, lots of people do particle tracing. The key difference is where do you stop the integration? When you're backward integrating, yes, I agree with you. Backward integrating is the way to go.
Yeah.
Where do you stop the integration?
Yeah, once you're in the magnetosheet.
No.
Then you know.
Once you're in a current sheet.
Oh, you're already through the current sheet.
No, you're not.
The magnetosheet.
No, you're not. That's the point. I think that's the key difference. You have to stop the integration before you penetrate this current sheet. And otherwise you wouldn't capture this. This is not you know, what are you gonna do up here? I mean, you're just gonna kind of go into the magnetosheath where the boundary condition is completely wrong for your guiding center. For the guiding center piece of the simulation. So the whole point is you have to stop at the current sheet. You can't just arbitrarily say, okay, I'm gonna wait till I'm in sheath like, or you have to keep track of where the guiding center theory is breaking down. And by the way, you would not reproduce the triple dispersions unless you did that. And so I think that's that's the key thing is we have to, what we thought we were gonna do is basically just do drift kinetics everywhere. But you run into this problem of how do you specify the boundary conditions? And it can't just be the solar wind, so why would you stop at the magnetosheath? Why wouldn't you just why don't you just go all the way through the bow shock into the solar wind?
Well, you stop at the magnetosheath because you know it's a Maxwellian distribution there, and you know the temperature.
It's a Maxwellian distribution here too.
Sure, you could do that, but most particles will not even go there, I mean, but there's.
Yeah, they would. Actually, you'd be surprised. A lot of particles just penetrate.
Yeah, ultimately, they all come from the solar wind, that's true.
But they don't just come from the solar wind, they get processed through the bow shock, then they get processed through the magnetosheath. Anytime there's a current sheet, that's where your guiding center theory is breaking down. You can't just integrate through those things. I mean, that's the key point. You can't just integrate through the current sheets. And so, I leave open the possibility that we don't understand these current sheets, I mean, these could be wrong. But we have to deal with them.
So how do you know what the distribution function in the current sheet is? I mean, it's actually, we're not.
Yes, that's the question. That's exactly the question. How do we know what the distribution function is in the current sheet?
Get the conclusion that your distribution is correct. You stop there. What distribution function do you assume to be?
Okay, so what I assume is that once I stop the integration, the distribution function is an isotropic Maxwellian at whatever the density and temperature is at that point where I'm stopping. And that is the best anyone can do.
In the current sheet.
Outside the current sheet. So there's
On the magnetosheath side or on the other side?
on the other side,
Inside magnetosphere.
inside the magnetosphere.
Right, that's the point is that the method.
You can't go through it. You can't go
Yeah,
past
the
it.
method isn't valid if you try to go through it. That's his point.
Yeah.
And so, yeah, it's raised a lot of questions that are very hard questions to answer, and we don't know the answer to that. I mean, somehow we have to make this kind of kinetic MHD model work, we have to have some kind of model of what the current sheets are producing in terms of guiding center distributions just outside the current sheet. And there are people working on this, like for the bow shock, you have drift kinetics outside the bow shock, but there's, particles get gyrophase dependent reflection and all kinds of stuff happening in the bow shock. And people try to come up with models for what is the appropriate guiding center distribution that the shock is producing upstream. And we can think about this as well. If you did this in the bow shock, what are you going to get? You're going to get particles streaming upstream of the bow shock. Particles will stream upstream of the bow shock, and they will drift perpendicularly as they're streaming. So you get time of flight effects, and that should sound familiar. That's how you get the foreshock. So you could actually mock up an ion foreshock by just letting particles stream up. And then you get parallel temperature anisotropy. I'm really going, haywire here, but I mean, there's lots of things you could do in this simple model that would reproduce more realistic looking stuff in the magnetosphere without going to a full particle model. All right, I think it's time for me to stop, but I just wanted to say, you can do play the same games in the tail. And reproduce things like velocity dispersed ion structures. We can even reproduce this mysterious gap that people have seen that is unsolved between the stuff that's happening way down the tail and the velocity dispersed ion distributions and the central plasma sheet. That's been a point of, that's been kind of a mystery, but it just sort of came out from this because this is a longer discussion. But what happens during the growth phase, at least according to this MHD model, after a long period of northward IMF conditions, is that you get a thinning in the near Earth plasma sheet. Everybody agrees with that. At some point, you get some thinning here. But way down the tail at about 100 RE, there's also often an X line. And from the earliest days of looking at these VDIS, people have estimated their distances to be at about between 50 and 100 RE. And that's been a totally separate, reconnection is way out there, but other people think it's closer in. But clearly in the simulation, we're seeing the guiding center theory break down deep in the tail as well as close during the current sheet fitting process. Okay, and I think this is gonna be my final one. What about the wave picture? How does, so we have these two pictures. I've shown you a bunch of particle, guiding center and particle precipitation simulations in background fields. We can actually calculate the bending term in Hall MHD that generates the field of line currents coming from the reconnection sites, just from the background MHD. So you can calculate the current density and see how the current density varies along the magnetic field, and that should be the rate at which the bending of the field is generating field of line current. You just calculate that. This is what we get. And so at exactly the locations from these magenta spheres where guiding center theory is breaking down, that's also where we start to get these Hall generated field of line currents during the growth phase. So this is prior to reconnection, by the way. So prior to reconnection, we have field of line currents, intense field of line currents being generated at that current sheet where guiding center theory is breaking down. So that would lead us to think that we would expect to see an auroral signature of those things during the late growth phase of the substorm. So that's very interesting. So I don't have time to go through all the MMS stuff, unfortunately, but just in case anybody is interested, we've been thinking a lot, working with Jason as well, on how we validate, how we make measurements of the distribution functions on scales that are relevant for these things like phase mixing, Landau damping. How do we test some of these models? And there's a lot of effort being done with MMS to try to do that. Using techniques that are more of the sort of cartoon picture of Landau damping, where you have a quasi-linear plateau that you're trying to measure. But the phase mixing is much more challenging. And I think, and people are moving in that direction as well, trying to see if we can actually measure the phase mixing. But we don't, even with MMS at 30 millisecond resolution or 7.5 millisecond resolution, it's not enough. So we've been thinking about how to use machine learning, in particular physics-informed machine learning, to increase the resolution of particle data. And it's a classic inverse problem where the basic problem is you have particle spectrometers with high voltage power supplies stepping up and down, up and down, up and down over some time. This is 30 milliseconds. And so this energy sweep time is sort of the minimum time resolution that you can measure the distribution function. Everything gets smeared over that time scale. But what you would like are measurements at these points, kind of instantaneous measurements of the whole energy spectrum. So how do you do that? One way to do that is, as Jason has been demonstrating now, this equation is very well satisfied. And so we all agree the Blathoff equation is a good physics model, right? And so if we have the electric field and the magnetic field at much higher time resolution than the particle data, we can use this information in the loss function of a neural network to guide the data. And so, we have these observations, and then we basically have at all these points, we just require that this equation be satisfied in the loss function. So the neural network is being trained to satisfy this constraint in the loss function. And when we do that, just for a simple toy model, here's a nice example of this. So if we just have a parallel electric field that's varying sinusoidally on the time scale of the sweep, and the phase space density is sort of sloshing back and forth on that time scale, this is what FPI would see, an aliased picture, because it's combining these two things into a single sky map. So an oscillating parallel current would turn into a temperature anisotropy for FPI. But this neural network can actually recover this just from the data from the sweep and the physics constraints using the measured electric field and magnetic field. This is very preliminary, but we're working on trying to apply this to the real MMS data. The problem with it is it's very, so the problem with these is that pins in general is that they're very expensive to train. So, back in the day, I think when these were first being explored, people were trying to use them to solve partial differential equations and say, well, can we just sort of have a co-location method where the neural network is just the function that we're optimizing to satisfy the partial differential equations. And it turns out to be a horrible PDE solver because it takes so long to train the neural network. And every time you have a new initial condition and boundary condition, you have to retrain it. But it's really good for these kinds of inverse problems when you're trying to fit sparse data to some function. And so I know there's a lot of interest here in machine learning and MMS, so we would really love to work with anybody who's interested in applying these kinds of things to MMS.
I'll give the lights to your question.
Okay, I think that is all I have time for. So thank you very much for your time.
People take the following approach to run your MHD simulation globally, then de-resolve it by like a factor of 4 in each Cartesian direction, and then you have a low spatial resolution kinetic MHD simulation, and use some Cultron's equation, and then you use that to calculate your heat flux. So you could kind of couple, you wouldn't capture reconnection layers, but you might, if you're looking to get large spatial structures and the influence of some of this kinetic physics, it might be a way to.
Yeah, so I think the issue with that is it seems like we have to resolve the current sheets somehow to get the right answer. And what you do with those current sheets actually has a big impact on what those ion dispersion signatures look like. They're sensitive to that. So how, those overlapping dispersions are what are giving you the heat flux. So I feel like the heat flux in the kinetic MHD region is being determined by the structure of those current sheets. That's the basic problem.
We're a bit over time as well for you to get back. We have some questions, but in case there's questions, take offline, wait there. And let's thank John one more time.